Imagine you have a box of your favorite marbles. In mathematics, that box is what we call a set. A set is simply a collection of things, grouped together because they share some property or just because we decide to put them together. Each individual marble inside the box is called an element of the set. Now, for our journey through calculus, the things that we will collect are almost always numbers. And the giant box that holds all the numbers we care about is called the real number line. Think of it as an infinitely long, perfectly straight ruler, where every single point on the ruler is a number. This line is our universe, the complete collection of all real numbers. Why do we even bother with this idea of sets and a number line? Because calculus is the study of how things change, and to describe change, we need to be incredibly precise about which numbers we're talking about. A function, which is the most important idea in this entire course, is a rule that takes an input number from one set and gives an output number in another set. To even define a function, you must first define the sets it works on. The number line gives us a map to point to a specific input, like pointing to a location on a street. Without sets, we couldn't say all positive numbers or the numbers between 0 and 1. Without the number line, we couldn't visualize a number getting closer and closer to another, which is the very heart of a limit. Let's build this idea from the ground up. First, forget the idea that a number is just a symbol. A number is a position on the number line. The number 0 is the starting point, the origin. Positive numbers are steps to the right, and negative numbers are steps to the left. Every single point on this continuous line is a real number. Now, a set is simply a collection of these positions. We can describe a set by literally listing its elements inside curly braces. For example, the set containing the numbers 2, 4, and 6 is written as 2, 4, 6. We have a special symbol to say something belongs to a set. It looks like a rounded E, and we say is an element of. So, 2 set membership symbol, 2, 4, 6, it means 2 is an element of the set containing 2, 4, and 6. It's just a quick way of saying a marble is inside the box. Let's solve a concrete, everyday problem. Imagine you have a medical freezer that must keep vaccines safe. The safe temperature range is from -5 degrees Celsius to +5 degrees Celsius. We can represent this rule perfectly with our new language. The set of all safe temperatures is every single point on the number line between -5 and 5, including the endpoints. We can even shade this entire interval on the number line to see it. Now, suppose you take a reading and the thermometer shows 3 degrees. Is that safe? We simply ask, is 3 an element of our safe temperature set? Yes, it is, because it lies in the shaded region. What if the reading is 7 degrees? 7 is not in the shaded region, so it is not an element of the set, and the alarm should sound. Imagine a special box. You drop a number in the top, gears turn inside, and a new number pops out the bottom. That box is a function. More precisely, a function is a rule that connects 2 sets of numbers. The first set, called the domain, holds all the allowed inputs. The second set, called the codomain, holds all possible outputs. The crucial rule is this: for every single input you put in, the function gives back exactly 1 output. You can't put in the number 5 and sometimes get 10 and other times get 12. It's a consistent, predictable machine. We often give the machine a name, like f, and we write f of x to mean the output when the input is x. Why build such a machine? Because the world is full of relationships where one thing depends on another. The distance a car travels depends on its speed and time. The area of a square depends on the length of its side. A function captures this depends on idea perfectly. It lets us model cause and effect with mathematics. If you know the rule, you can predict the outcome for any input. You can ask what-if questions. What if the side length is 5 meters? The function machine gives you the answer, an area of 25 square meters. This is the first step in calculus, understanding how one quantity changes because another one changes. A function is the tool that describes that changing relationship. Let's open the machine and see how it works. First, you pick an input. This input must be a member of the domain, the set of all numbers the machine is built to accept. You feed this input, which we call x, into the function f. Inside, the machine follows its rule. The rule could be something simple, like to square the number, or more complex. After applying the rule, the machine produces the output. This output is called the image of x under f. The notation f of x is just a neat way to package this whole process. The letter f is the machine's name, and that x in parentheses is the input we're giving it. So, f of x equals the output. It does not mean bef times x. It's a single, unified symbol for the result. Let's use our function machine to solve a real problem. Imagine a taxi company charges a $3 flag-down fee, and then $2 for every kilometer you travel. The total cost depends on the distance. We can build a function for this. Let the input, x, be the distance in kilometers. The rule is, multiply the distance by 2, and then add 3. So our function is f of x equals 2x plus 3. Now, what if you take a 5-kilometer ride? We feed the input 5 into our machine. The rule says 2 times 5 plus 3. That's 10 plus 3, which equals 13. So, f of 5 is 13. The output is $13. The function gave us a clear, single answer for our what-if question. This same method, define a rule, then plug in a value, works for any function you'll meet. Imagine a function as a machine with a strict gatekeeper at the entrance. The domain is the complete list of all the inputs that the gatekeeper will actually let inside. It's the set of every number you are allowed to feed into the function without causing an error. Think of it like a roller coaster with a height requirement. If you're too short, you're not in the domain. For a simple, friendly machine like f of x equals x squared, the gatekeeper is very relaxed. You can hand it any real number you can think of, -2, 0, pi, a million, and it will happily square it and give you an output. The domain is all real numbers. But for a pickier machine, like the square root of x, the gatekeeper gets strict. If you try to hand it a negative number, say -4, the machine jams. It doesn't know how to give you a real number output. So, the domain shrinks, it's only the non-negative numbers. Knowing the domain is like having a map that shows you exactly where a function is safe to use. Its main job is to prevent what we can call a machine jams, those moments where a calculation breaks, like trying to divide by 0 or taking the square root of a negative number in the real number system. Without a domain, you'd be wandering blindly, trying inputs that lead to mathematical nonsense. The domain also tells you where the function lives on the real number line. It's the function's entire universe of valid inputs. This is a foundational idea. When you later study limits, which ask what a function does as you approach a point, you first need to know if that point is even in the function's neighborhood. When you draw a graph, the domain tells you how far left and right your pencil should go. It's the very first question you ask about any function: what can I safely put into this? To find a function's domain, we play a game of kick-out. We always start with the biggest possible set, the entire real number line, from -infinity to +infinity. This is our initial guest list. Then, we look for troublemakers. We scan the function's rule and kick out any input that causes a mathematical crime. There are two main crimes to look for right now. The first is division by 0. If you see an x in the denominator, like in 1 over x, you must kick out the x value that makes the denominator 0. The second crime is trying to take an even root, like a square root or a fourth root, of a negative number. If you see a square root, like in the square root of x, you must kick out any x that makes the stuff inside the root negative. Whatever numbers survive this purge, whatever is left on the guest list, that is your domain. Let's see why this matters with a real problem. Imagine you drop a rock from a certain height, h meters, above the ground. Physics gives us a function to find the time, t, it takes to hit the ground. The formula is t equals the square root of h over 5. Now, let's find the domain of this function. We start with all real numbers for the height, h. But we see a square root, so we must kick out any h that makes the inside, h over 5, negative. Since 5 is positive, h over 5 is negative only when h itself is negative. Can a height be negative? No, a negative height would mean you dropped the rock from below the ground, which doesn't make physical sense. So, we kick out all negative numbers. The domain is all non-negative real numbers, h is greater than or equal to 0. Imagine you have a function machine. You already know the domain is the set of all allowed inputs you can feed in. The codomain is the full menu of possible outputs the machine could ever give, even if it never uses some of them. The range is different. The range is the actual set of outputs the machine really produces when you run every single input from the domain through it. Think of it like this: you take every number in the domain, drop it through the function, and collect all the results. That collection is the range. It's like shining a light through the domain and seeing where its shadow lands on the y-axis. The range is exactly that shadow. Why do we care about the range? Because it tells you what a function can and cannot do. If you're solving an equation like f of x equals 5, the range instantly tells you whether a solution even exists. If 5 is not in the range, you can stop looking. It also helps you understand the function's behavior. For example, knowing that the range of x squared is only non-negative numbers tells you that squaring a real number never spits out a negative. This is a powerful check. Later, when you study inverse functions, the range becomes the domain of the inverse. So understanding the range is like knowing the function's true reach. Let's see exactly how to find the range. We begin with the domain, which for our main example is all real numbers. Picture the entire x-axis. Now, take each of those x values and apply the function. For f of x equals x squared, we square every single real number. What happens? A positive number squared stays positive. A negative number squared also becomes positive. 0 squared is 0. So every input, from negative infinity to positive infinity, lands on a y value that is either 0 or a positive number. No input ever lands on a negative y value. So the range is all y such that y is greater than or equal to 0. We write this as the interval from 0 to infinity, with a square bracket at 0 to show it's included. This is a subset of the codomain, which we usually set as all real numbers. The codomain had negatives available, but the function never uses them. Let's ground this with a real problem. Imagine you throw a ball straight up. Its height in meters after t seconds is given by h of t equals 20t minus 5t squared. The domain here is not all real numbers, because time starts when you throw it and ends when it hits the ground. Let's say the ball is in the air from t equals 0 to t equals 4 seconds. So our domain is the closed interval from 0 to 4. Now, what is the range? What height does the ball actually reach? We push every time in the domain through the function. At t equals 0, height is 0. At t equals 4, height is also 0. The function is a downward opening parabola. Its maximum height happens exactly in the middle, at t equals 2 seconds. Plugging in 2 gives us 20 times 2 minus 5 times 2 squared, which is 40 minus 20, so 20 meters. We already know the domain is the set of all possible inputs a function can accept. But some inputs cause trouble, they break the rules of ordinary arithmetic. The two most common rule breakers are dividing by 0, and taking an even root, like a square root, of a negative number. If you try either one, the function doesn't produce a real number output, so those x values are kicked out of the domain. Think of them as holes or gaps on the number line where the function simply does not exist. Why do we care about these forbidden inputs? Because if you accidentally plug one in, you don't get a useful answer, you get undefined. More importantly, these restrictions shape the entire graph of the function. Near a division by 0 point, the graph shoots up or down forever, creating an invisible wall called a vertical asymptote. The function can never touch or cross that wall. And because the function can never land on certain y values near that wall, the range, the set of possible outputs, gets restricted too. Understanding these restrictions is like reading a map before a journey, you need to know where the bridges are out. Let's derive the domain for a rational function like 1 over x minus 2. The rule is simple, a fraction is only defined when its bottom, the denominator, is not 0. So we set the denominator x minus 2 not equal to 0, which means x cannot be 2. Every other real number is fine. Now, what happens to the graph near x equals 2? As x creeps closer to 2 from the right, say 2.001, the denominator becomes a tiny positive number, so the whole fraction becomes a huge positive number, it shoots up. From the left, like 1.999, the denominator is a tiny negative number, so the fraction becomes a huge negative number, it plunges down. The line x equals 2 is a vertical asymptote, a boundary the curve approaches but never touches. The word asymptote comes from Greek meaning not falling together, the curve and the line never meet. Imagine a ball thrown straight up. Its height above ground is modeled by a function of time, but let's use a simpler rational function to see the idea, height equals 1 over t minus 3. Time t must be 0 or positive, we don't allow negative time. But at exactly t equals 3 seconds, the denominator becomes 0, so the function is undefined. That's the moment the ball would hit an invisible barrier and its height becomes infinite, physically impossible, so we restrict the domain to all non-negative t except 3. What about the range? As time approaches 3 from the left, height plunges to negative infinity, from the right, it soars to positive infinity. The function can output any real number except 0, because 1 over something is never 0. So the range is all real numbers except 0. The same method, set denominator not 0, inside even root non-negative, solves any domain problem. Imagine the graph is a solid object sitting on the xy plane. The domain is every x value the graph covers. Picture shining a bright flashlight straight down from above the graph. The shadow it casts on the x-axis is exactly the domain. It's the set of all x coordinates where the graph exists. Similarly, the range is every y value the graph reaches. Shine a flashlight from the side, left to right. The shadow on the y-axis is the range. We call this the flashlight shadow method because it turns a visual picture directly into the sets of numbers we need. When you have a function's formula, finding the domain often means solving tricky inequalities or checking for division by 0. But a graph shows you everything in one picture. You can see exactly where the function lives on the x-axis, including any gaps or jumps, without doing any algebra. This is especially powerful for piecewise functions, which are made of different rules glued together. The flashlight method lets you read the domain and range directly. even when the function is broken into pieces or has sudden stops. It turns a visual inspection into a precise answer, which is a huge time saver and builds deep intuition for limits and continuity later. Here's the step-by-step method. For the domain, imagine a vertical line sweeping from left to right across the entire graph. Every time that vertical line touches the graph, the x-coordinate at that spot belongs to the domain. If the line passes through a gap or an open circle, those x values are excluded. The domain is the union of all intervals where the vertical line makes contact. For the range, do the same with a horizontal line sweeping from bottom to top. Every y-level where the horizontal line hits the graph is in the range. This works because a point is on the graph exactly when its x is in the domain and its y is in the range. The sweeping line tests every possible input and output visually. Let's apply this to a concrete piecewise function. Suppose f of x equals x plus 1 when x is less than 0, and x squared when x is greater than or equal to 0. The graph is a straight line with slope 1 on the left side of the y-axis, and a parabola opening upward on the right side. Shine the vertical flashlight from above. The shadow covers the entire x-axis because the line extends forever left and the parabola extends forever right. There are no holes or jumps in the x direction. So the domain is all real numbers. Now shine the horizontal flashlight from the side. The line on the left goes down forever, so it covers all y values. But wait, the function switches to the parabola at x equals 0. And the parabola's lowest point is at 0. The line part for negative x gives y values less than 1, but the parabola never goes below 0. When we use a function to model something real, like a thrown ball, the pure math often gives us a formula that works for any number. But the real world slaps handcuffs on it. The domain becomes only the time from when the ball leaves your hand until it smacks the ground. The range becomes only the height the ball actually reaches, from ground level up to its peak. So domain and range aren't just abstract ideas. They are the real, physical limits of the situation we are describing. Why do we care about these limits? Because they answer the questions we actually ask. When will the ball hit the ground? That's the end of the domain. How high did it go? That's the top of the range. If we ignored the real-world domain and plugged in a negative time, the formula might happily give us a height, but it would be nonsense, like saying the ball was underground before you even threw it. The constraints keep our model honest and useful. Let's build this from the ground up. Imagine you toss a ball straight up. Its height over time is a parabola. We can write a simple model, height equals negative 5t squared plus 20t. At t equals 0, height is 0, the moment it leaves your hand. The domain starts there. The ball rises, slows down, and at its peak the slope of the curve is flat. That gives us the maximum height, the top of the range. Then it falls back down. The domain ends when height hits 0 again. We find that by setting the height equation to 0 and solving for the positive time. The range is every height between 0 and that peak. Let's solve a concrete problem. You throw a ball with a height function h of t equals negative 5t squared plus 20t. First, when does it land? Set h of t to 0. Factor out 5t to get 5t times for minus t equals 0. The solutions are t equals 0, the start, and t equals for seconds, the landing. So the real-world domain is all t from 0 to 4. Next, the maximum height. The peak of a parabola is halfway between the roots, at t equals 2 seconds. Plug that in, negative 5 times for plus 20 times 2, which is negative 20 plus 40, giving 20 meters. The range is all heights from 0 to 20 meters. The math gave us a formula, but the real world drew the boundaries.